So, okay, let us continue our lectures. And the next speaker is David Krieg. So, David, you are welcome.
Thank you. Yes, I want to thank you for inviting me. I think it's a really nice workshop here, school and conference, and it got much bigger than I expected. And yeah, it's quite an honor to have such a big slot in this conference. So thank you. And also thanks for the people who congratulated me on my prize. And so we already heard quite some talks about the connection of the Cadison-Singer solution and of matrix concentration results with sampling problems, also by my co-author Mario. And so I decided to talk about some different problem. So this is now not connected, not so much connected to this. And first of all, I try some new program here. I hope you can all see my slides and what I'm writing. Can you see that?
Yes.
Okay, good.
This yellow marking. Yes, we can see.
Okay, very good. Yes, and so I'm going to talk about the recovery problem, but for classical Sobolev spaces with isotropic smoothness. And as you know, or as you might guess, so this problem is well studied if you think about optimal sampling recovery. But we were interested in the question, what can we say for certain types of given information? For example, random samples or just an arbitrary set of sampling points. How can we determine the quality of such sampling sets? And so this is the most part is joint work with Matthias Sonnleitner. He's a PhD student of Eike Hinrichs at my university in Linz. And later I will come to some very new stuff, which is also with Erich Nowak. Okay. So what's the problem? Let me recall the setting, which is the setting of information-based complexity. And so we have all the time, we have a bounded and convex set in RD. And for this talk, you should rather imagine something like D equals, this one's 3 or something. So it's, of course, it's also true for large dimensions, but the results won't be so useful if you have D equals 360 or something. Yeah. Okay. And now we assume that we have some normed space of functions on this domain. Let's say real valued or complex valued. I think in this talk it's real valued. And we assume that this normed space is contained in LQ with respect to the classical Lebesgue measure. And then we have a set of sampling points. So N in my talk is always the number of sampling points in the set omega. And for me, a recovery algorithm is just a general mapping of this form. Take the yellow pen. So we just compute the function values at the given points and then somehow map it back to the space LQ. And for the most part of the talk, actually for all of the talk today, but tomorrow we will change. We will consider the worst case error in a deterministic setting. So what we are interested in is we take the distance of f and our recovery in the space LQ, and we take the worst case over the unit ball of this normed space of functions. And then we are interested in what is the best possible worst case error that we can achieve with the fixed point set P. So this is what I denote by the error of the point set P when recovering functions from F in LQ. Yes, and for the people who were away in the break, I sent you a link with my slides, so you can download them if you want. And if somebody gets lost in notation, you can look it up again. Okay, and now I've first assumed that the recovering map phi is just any map which makes a function out of our samples, but sometimes it's preferable if the algorithm is linear. So I also introduced this notation with the extra lin here, where I only allow algorithms which are linear and take this set of sampling points. Yeah, so this is obviously larger than the notion without the lin. Okay, so this is the basic setting, and as I said, I will talk about Sobolev spaces. So most of you probably know them, but it's since it's also a school, I want to recall all the basic stuff too. So the Sobolev space with smoothness S on the domain omega, let's say integer smoothness and integrability P between 1 and infinity. So it just consists of all functions in LP such that derivatives up to order S, so these partial derivatives, they should be also in LP. And the partial derivatives meant in a weak sense. Yes, but it would also make sense if you consider classical derivatives, then you just don't get a Banach space. Okay. Yes, and this is a Banach space if you take as a norm just the sum of all LP norms of the derivatives. No, okay, yeah, I only take the ones with the largest order and the one with the smallest order, but you can optionally, you may add the ones in between. It's an equivalent norm. Okay, so this is a Banach space, and we will always assume that the smoothness is larger than D over P. So that by the Sobolev embedding theorem, the functions are smooth, are continuous and bounded. Okay, and as I said, the problem is well studied for optimal sampling points. So classically, one is interested in minimizing this error over all point sets P with a fixed cardinality. So we additionally now take the infimum over all point sets with cardinality at most n. And yeah, then we have this quantity, which was sometimes called nonlinear sampling numbers. Of course, we might also define it with the extra lin. Yes, and this theorem here on optimal sampling points, you can find it, for example, in a paper by Erich Nowak and Hans Triebel. Most of it is already contained in an earlier paper by Wendland, Ward, and Narkovic. And it's it says that the optimal order of convergence of this non-linear sampling numbers is like this. So this little plus here means that V plus is just the maximum of V and 0. Okay, so this is the order. And of course, this is known from even earlier results for special domains like the cube. So this is a very old and classical result. The new thing in these papers, which I cite here, is just that the domain can be quite general. Yeah, actually, they consider Lipschitz domains. Here we consider only convex domains, which are automatically Lipschitz domains, because we will need it for some of the results, which I will show you. Yes, and so this notation means the left-hand side is bounded by a constant multiple of the right-hand side and vice versa. And this constant may depend on everything but n. So it may depend on the domain, on the dimension, on p and q and everything. It's just the order in n. Yeah. And how is this bound achieved, the upper bound? You can take a polynomial reproducing map, which was introduced by Wendland. You can find it in his book. And you can use this kind of algorithm for equispaced points, more or less. If the domain is strange, you may not be able to put equispaced points in the domain, but something like it. Yes, and this algorithm is a linear algorithm. So I might also put the lin here in the result, and I get the same. The lower bound is clear, of course, and the upper bound is because the optimal algorithm in the proof is already linear. Yes. And also, I wanted to say, feel free to interrupt if you have some remark or question. Yes. So here are my questions. Now we suppose that we cannot choose the sampling points. And we ask ourselves, is there a way to determine the quality of any given point set? How can we measure that? If we get just some data which we cannot choose, what can we say about the quality of this data? And this is somehow close to what Albert in his talk called the passive setting. So the difference between the active setting and the passive setting, where you can choose your sampling points or you cannot. And so I want to turn to this passive setting. And yes, the second question, which is of course quite related, is how do point sets have to look like in order to get the optimal order of conversions? So we know that equispaced points are good, but is this already it, or are there more choices? Do we have more flexibility? And the third question, which was our original motivation and which already appeared in Mario's talk quite often, is the question, how good are random sampling points? So how, if we just get our informations by independent and uniformly distributed points on the domain, how much do we lose in comparison to optimal information? This is somewhat also inspired by what I read very superficially in all these papers on machine learning and so on, because this is the standard model somehow that that the sampling points come in IID and you cannot choose it and you have to cope with it. Okay, so those are the three questions, and here's a remark. So there are already many authors who use the radius of the largest hole in the point set, which is the covering radius, to bound the error of the sampling-based algorithm for whatever problem they consider. And for the LQ approximation problems, intuitively one would think that like this is okay. If you consider something like L infinity approximation, then you should really have a good covering radius. So if this is your domain, then the points should cover the domain quite well. But if you consider, for example, L1 approximation only, then it should be okay if there is some larger hole where only few points are, because this means that locally your approximation will be worse, but as you measure the error as L1 norm, then this should average out somehow. So what we want to see in the result is that yes, for example, for L1 approximation or for integration, the error should not depend on covering radius, but rather on some kind of average hole size. Yes, and so the first question was, how can we determine the quality of a given point set? Some notation first. I write the distance of x to the point set is just the minimal distance, of course, from x to an element of the point set. So here are my points. And for example, here is x. And then the distance to the point set is like this. So alternatively, it's the radius of the largest ball around the point x that does not intersect the point set. And we will call such this largest ball, we will call it a hole in the point set. Okay, and the covering radius then is just the radius of the largest hole. So in other words, the L infinity norm of this distance function. Okay, and now instead we can also take the L gamma norm of this distance functions for some gamma between 0 and infinity. And this quantity also appears in the literature and is called distortion of the point set. Or actually we found it in the context of quantization theory. So it's rather called the distortion of the quantizer that belongs to the point set. So what's a quantizer? Quantizer, you can just imagine like this is the error that you make if you round every point in the set to the nearest point. If you like replace an element x of the set omega by the nearest element of the point set p, then this is the average error that you make. So that this is called distortion, and they have this notation here. Okay, and yes, there's not much more to say. And now we come to the first characterization for general point sets, and for q greater or equal than p. So if you approximate in LQ and the Sobolev space has integrability p smaller than q, then the error is indeed determined by the size of the largest hole. So we get that for any point set, the error is given by the covering radius to some power, up to multiplicative constants which do not depend on the point set. Yeah, also not on the size of the point set, of course. Yes, and this is not really new. So I cite the same papers here. They didn't write it down this way, but you don't need a new idea to get there. So the upper bound is achieved by the same algorithm, this polynomial reproducing map, which is linear. So you will get the same result for linear algorithms for the sampling numbers restricted to a point set. And yeah, that's it. So the new thing is now the case q smaller than p, and you might already have guessed that now we have on the right side not covering radius, but distortion. So if Q is smaller than P, then the error is characterized by the gamma distortion of distance function. So by the L gamma norm of this distance function to the power S. Yeah, so it's rather the average hole size counts and not the largest hole. And yeah, again, the hidden constants depend on everything but P. The algorithm is not the same anymore, but it's related. So roughly, if you are given the point set, you construct from that point set some special covering of the domain by cubes. This is the algorithm which we considered. And then in each of the cubes, you apply this polynomial reproducing map by Wendland. Yes. So I will come back to the algorithm later. And also this algorithm is linear, so we get the same result for the linear sampling with. Okay. And yes, now since this is a school, I want to present the proof more or less. And I will make a restriction to avoid some boundary issues, which are just technical. I will consider instead for this talk the class of functions with zero boundary condition. So which I denote with such a dot on the W. So now this are all functions in the Sobolev space on the whole RD, which are zero outside the domain omega. And yeah, just a remark for this modified class, we do not need the convexity of the domain anymore. So the convexity comes in combination with this boundary issues, of course. And so in the proof, you might just imagine omega as some bounded open set. Okay, and the first ingredient of the proof is the radius of information, which is widely used in information-based complexity. What's the radius of information? So if we have, like in the beginning, a non-space of bounded functions on the domain omega, in this case, it would be just a Sobolev space with zero boundary condition. B of f shall be the unit ball. Then the radius of information with respect to LQ, and the point set P is called the information, then is defined as the maximal LQ norm of a function from the unit ball of the space, which vanishes on the point set P. Yeah, so this is looks somehow like Gelfand numbers, where you take the maximal norm in some space for an element of the unit ball, which is satisfies some linear equation which leads to codimension n, and this is exactly like this, but now you fix some certain linear equation, namely f vanishes on the point set. Okay, and now the following lemma is quite important. You might also call it fundamental lemma of IBC, maybe. And it says that the minimal worst case error which you can achieve with the given information is basically the same as this radius of information. So it's the error is larger than the radius and smaller than 2 times the radius. And this is Yeah, I write it down here for the LQ approximation problem, but it's true for all linear problems, also integration problem, or could be some solutions to differential equations or whatever. Yeah, I forgot to write this down. So this is also for linear problems, you have such a result. And yes, you can find it, for example, in the book of Erich Nowak and Hendrik Wozniakowski, first book. And another remark, if F is a Hilbert space, then we have even equality. So the factor 2 is also gone. And yes, I want to show you the proof, because if you haven't seen it before, some of you will be bored because they know it very well. But if you haven't seen it before, it's something nice to take home. And so how does the lower bound work? So the statement that the minimal error is larger than the radius of information. Well, if you have such an element of the unit ball of the space, which vanishes on the points at P, we call it a Fooling function. Why do we call it a Fooling function? Because any algorithm of this form, so any algorithm which uses the given sampling points, it can, of course, not distinguish this function f star from its negative. The output is the same. And what does it mean? So for any algorithm of this form, the worst case error, so this term here, is the worst, oh, wrong pen. The worst case error is, of course, larger than just the maximum of the error if you input f star and if you input minus f star. And since the output for f star and minus f star is the same, then for one of the functions, you have to make at least the error equal the norm of f star. And so since you cannot distinguish f star and minus f star, the best thing you can do is to put your approximation equal to 0. And this gives you that for any such function, the error is larger than the norm of the function, so the error is larger than the radius of information as defined above. So quite simple. And the upper bound is also rather simple, but rather nice. And what do we do here? We consider an interpolatory algorithm. So for our approximation, we just take any function from the unit ball which interpolates the given information. So which for which the function values at the point set are equal to the data that you collected. And this exists, of course, and it requires only the given data. But I already have to mention, in praxis, this is often not feasible. Yeah, it's often not quite practical to find an interpolatory function which has a small norm in the given space. But sometimes it is. And yes, if you consider this algorithm, then we can consider its worst case error here, which is smaller than the supremum. So since the output here, this SP of F, is also in the unit ball of the space, then this difference is, of course, smaller than, and interpolates smaller than the supremum over differences of functions f minus g, like this, which do yield the same information and are both in the unit ball. because SP of f is such a function. And well, we call this function 2h, so h we just define as difference divided by 2. This is also in the unit ball, and this function has information 0. And so the supremum is smaller than if I take the supremum over these functions. And yes, and here the 2 comes in from this 1/2, so that I stay in the unit ball. And this is exactly the radius of information. Okay. So we wanted to prove something on the error for the given point set in the space WPS dot in LQ. And so instead, now we can consider this quantity, which is the same up to a factor of 2. So the supremum of LQ norms of a function which are in the unit ball of the space. So it satisfies these 3 conditions. So there are 0 outside omega and have information 0. So the function restricted to the point set is 0. Okay. And how do we do this? Yes, there comes in the result of Wendland and also other results. So what can we say about functions which have some scattered zeros, about the size of these functions? And for example, if the point set is of this form that we have the unit cube and we divide it into a constant number of subcubes. And if you have a 0 in each of these subcubes, then you can say that the maximal function values is bounded by a constant multiple times the seminorm of the space WPS. It's bounded in supremum by this. Yeah, the number of subcubes which you have to take depends on the smoothness, but that's it. Yeah, and I think this result is actually quite intuitive. If you have enough zeros which are spread somehow decently, and when you have small derivatives, then the function should be small. Okay, and well, how do you actually prove it? Well, you use a result of Wendland about these polynomial reproducing maps, and then you use results on best polynomial approximation for this space. So basically you find a polynomial which is pretty close to the function, and then you apply the polynomial reproducing map. It's not much to do if you have these results. Okay, and now we dive into the proof. So we now have our domain omega, and we have our point set, which you can find here in the picture, all the dots. And given a cube, we call it a good cube if in each of these subcubes, which I was talking about, you have a point from the point set or a point from outside. Yeah, the outside part doesn't matter for us because the function is 0 there anyways. Okay, and we call it good cube, of course, because then we have this kind of estimate from above. We can rescale it to the diameter of the cube, and then we get that and take the LQ norm. So the volume of the cube comes in again. And then we get if f is from our space and vanishes on the point set, NQ is such a good cube, then the LQ norm on the good cube is bounded by the diameter to some power times the semi-norm of the function on this cube. Okay, and now how do we proceed? For every point x in the domain, we now define the smallest good cube around this point. So we just take the infimum over all radius of cubes that just centered at this point and are good in the sense that we have enough well-distributed points around this. And yes, and we call these smallest good cubes, we call them Q of x and the radius R of x, so half the side length. And yes, for these smallest good cubes, we of course have the property from lemma 3, so this estimate of the LQ norm by the diameter to some power times the semi-norm of the function on the cube. And since we took the smallest one, we additionally have the property that there is some empty cube of the same size inside. Yeah, if we take the cube with radius R of x half around our point, then one of these subcubes must be empty because it's not a good cube. And we call this empty one, we call it Q star of x, and we will use it later. Okay, so now we have for every point such a small good cube, which contains an empty subcube of the same size, of the same order. Yes, and now what do we do? Now we pick some of these cubes such that we have an efficient covering of the domain. What do I mean by efficient covering? First of all, it has to be a covering. So we pick some points such the corresponding good cubes here cover the domain or the closure of the domain. And we additionally want the property that these empty cubes, which I talked about, are pairwise disjoint. And the third property is what I call the efficiency, namely every y in the RD is covered at most a constant times. So it is contained in the most 2 to the d good cubes, Qi. Yeah, and yeah, we didn't invent this kind of covering lemmas, of course. You probably all know the Vitali covering lemma, and a lemma of this spirit is also known, not precisely like this, but pretty close. And yes, yes, I wanted just to say how you can construct this covering actually. The construction is just like this. You take the, as first point, you take the one which minimizes the radius of the good cube. So the maximizes, sorry. So you take the largest good cube from the above construction, and then you take the next largest and so on. So you take outside of the cube which you already have covered, you take the one which maximizes this radius function. And this is well defined because the function is upper semi-continuous. And then you get these properties. You have to do some, yeah, it's quite elementary, but not a thing you can do in 2 minutes. Okay, and now we have this covering of the domain by good cubes in some efficient way. Very nice picture. And now we come actually to the proof, first of the upper bound. And yes, so we assume we do an upper bound on the radius of information. So we assume that f is from the unit ball of the space with 0 boundary condition and that it vanishes on the point set. Then we have to estimate the Q norm of this function, and it is because the cubes form a covering, of course, the Q norm to the power Q is smaller than just the sum of the Q norms on the cubes. And by the estimates, because they are good cubes, you get these estimates for the size of the Q norms. And now you do some Hölder inequality. The precise parameters are, of course, not interesting for this talk. You just do it in a way such that here actually the piece power of the semi-norm appears, so that they, in the end, they will add up nicely. And what remains is, yes, two parts. The one is, as I said, a sum of the semi-norms to the piece power. So this is basically the integral of the derivatives to the piece power over the cube qi. And since the covering is efficient, so we do not hit every point more than a constant times, this adds up nicely to some, to the, this is actually smaller than to the d, because we hit every point at most 2 to d times the semi-norm of the complete domain. And then to the q over p. So this is smaller than a constant because f is from the unit ball. And for the first part, what remains is the sum of the radio of this good cube. And the radius of a good cube is basically given as an integral of the distance function over the cube because of we have these empty cubes. This means that the distance function is on the NV cube is larger in size than the radius divided by some constant on a set of volume of the same order as the volume of the complete cube. So this is roughly this integral. And if you add them up, again, because of the efficiency, this is basically the same as the integral over the whole domain. So you get the desired upper bound that this is bounded by the L gamma norm of the distance function to some power. Yeah, gamma is this in the theorem. So like this. Okay. And now the lower bound. For the lower bound, we have to construct a Fooling function with a large norm. And you might guess that for this, we use these empty cubes inside the large cubes. So each one has an empty cube inside, whatever, which is of the same size up to a constant. And these are disjoint. And what do we do now? In each of the red cubes, we put a little bump. So we start with some non-negative smooth function with compact support, which is not 0. And we rescale it such that the support lies inside these empty cubes, which we have from our covering. And then we take a linear combination of these functions. So we just have many little bumps. And some computation shows how to choose the height of these bumps such that you get as large as possible LQ norm, and then you get actually the same lower bound as upper bound. Yes, and this finishes the proof. As I said, I made the simplification of the zero boundary condition because of technical issues, and what I also avoided was to actually prove the result constructively, but in the paper it's done constructively using this algorithm which I already talked about. So how does the algorithm look like in the general case? So for every x, we take q of x as the smallest cube with center x such that it contains a constant number of well-distributed points. So like before with this a point in each subcubes, but now in the sense of the covering radius. So the covering radius of the intersection of the cube and the domain should be smaller than a small constant times the diameter of the cube. The constant we have to choose adapted to the smoothness. And yes, and the covering works as before. So we choose x1 as a maximizer of this diameter of the good cube. Yeah, so the covering radius of the point set P1 intersected with the domain inside this cube intersected with the domain should be small. And then we use Wendland's polynomial reproducing map on this largest cube. So what is this map that I'm talking about all the time? So you proved that there are functions ux on the domain omega1, which I consider such that this recovery map here, this linear recovery map using the functions ux reproduces polynomial of degree s, like the smoothness, and such that its norm as an operator from L infinity to L infinity is bounded. Yes, and Wendland actually also tells us how to construct these functions. I think this is pretty close to the things you already heard. Now you want some reconstruction map which is exact on a given subspace. This time the algebraic polynomials, not the trigonometric polynomials like in the previous talks, and has some boundedness property. Yeah. Okay, and what does the algorithm do? Of course, for x in this first cube, we return the output of this polynomial reproducing map, and then we go on like this. So we choose x2, x is a maximizer of the diameter of the good cube on the remaining domain, and then we apply Wendland's polynomial reproducing map for this next domain, and so on. And this procedure terminates, and then you have your approximation. Okay, and okay, so somehow I don't see the chat, but I hope somebody would tell me if there are any questions. Okay, so here I will come back to the result. We have thus proven that if I define gamma like this, then the error of the point set is given by the L infinity norm or the covering radius of the distance functions to some power if q is larger than p and it is given by the L gamma norm of the distance function, or the distortion to the power s if q is smaller than p. And this may be extended also to non-integer smoothness and also to the quasi-Banach case. So p smaller 1 or q smaller 1 is also okay. And you may also prove it for the wider range of triple Lie spaces. And also for Sobolev spaces defined on compact Riemannian manifolds. So yeah, you can just lift the result. I mean, there's technical difficulties, but the idea is just lifting the result via a map to the Riemannian manifold. Yeah, and you can do similar such stuff for the integration problem, namely, so how's the error of the point set for the integration problem defined? You just take the infimum over all weights, AI, of a quadratic formula, the worst case error again. So you take the distance of the integral and the quadratic formula, worst case over the unit ball of the space, and optimize over the weights AI. And here you might also consider non-linear algorithms for the integration problem, but there's a really classical result by Smolyak and Bachwalov from 71, which says that the infimum does not change. It's the same for linear algorithms and nonlinear algorithms, so we don't need to define the other quantity. Okay, and for this integration problem, it turns out that we have the same bounds as for the L1 approximation problem. So one of the estimates is obvious. The integration problem is easier than the L1 approximation problem. If I'm able to approximate my function in the L1 norm, then I can also estimate the integral by computing the integral of my approximant. And the error will be the same and or smaller. And the upper bound is also clear from the proof, because I mean the lower bound for the complexity of the integration problem is also clear from the proof, because these Fooling functions which we constructed were all non-negative, so they also have a large integral. Okay, so I can write it down explicitly. So the error of the point set for the integration problem is basically characterized by the norm of the distance function in L gamma to the S, where gamma is equal to S times 1 minus 1 over P to the minus 1. For P larger than 1. For P equals 1, gamma is equal to infinity. Okay, and for today, I would just want to add some open questions. The rest has to wait till next time. Namely, first some questions which are pretty close. We didn't get the same result for the integration problem for general triple Lie spaces, because then we didn't work. If we consider triple Lie spaces, we weren't able to work with such bump functions, but rather with wavelets, and those have finally a large LQ norm as wished for, but they have integral 0, so this didn't work out. But I guess it should hold true for these triple Lie spaces. And the second thing is we assumed that the domain should be convex, but I would think that is just a technical assumption. And the result actually holds for more general domains, for example, all bounded Lipschitz domains. By the way, I didn't tell you where the convexity comes in. The convexity comes in if you consider the intersection of the cube with the domain, then you want that this intersection still satisfies some interior cone condition with a nice radius in order to apply the results of Wendland for polynomial reconstruction. And this isn't the case for Lipschitz, general Lipschitz domains, but it's the case for convex domains. Okay, a little bit of a harder question would maybe be, are there similar estimates for the quality of general point sets that take better care of the tractability issues, so of the dependence on the dimension? So, I mean, we had this error, like we have it characterized by some gamma norm of the distance function. But as you already saw in the covering, there was some 2 to the d, so there are some exponential constants in the dimension. And well, there is some nice work on, but it's on optimal point sets by Mario also, and Erich, and Eike Hinrichs, and I think also Henrik Wozniakowski, which give lower bounds, which more use the distance function in the L1 metric. So one could ask maybe whether this is a better quantity to describe the error. Of course, it makes no difference if we consider the order of convergence, but it makes a huge difference in large dimensions. But I don't know whether then the exponential constants disappear. I don't probably think so. Okay, and the fourth and probably even harder question is, do we have a similar result for function spaces of mixed smoothness if we replace the Euclidean distance by some kind of hyperbolic distance? You might imagine maybe that the point set is good for approximation problems on mixed smoothness spaces if the covering radius with respect to small hyperbolic crosses or something is small, but this just, yeah, I guess. So this is a big task. Okay. Okay. Question 2 and question 3 will come next time. So the question for the optimal order of convergence, how do point sets have to look like? And the question of the quality of random point sets. And then we will also consider a different error criterion closer to the talk of Albert, so the randomized error, but also this kind of. Okay, then thank you very much. This is it for today.
Thank you, David. And now we have time for questions and comments and remarks. Are there any questions? Comments? Okay, maybe the questions and comments will be tomorrow during the next lecture. But before we stop, I want to announce some schedule changes. So tomorrow, these are minor changes, but anyway. So tomorrow we will have first the 2 talks of Tina Ulrich. So the first one will begin at 15 Moscow time at 15 as usual, and will end at 17. So 2 lectures, and there will be a break maybe after 15 minutes or so. And the David's talk will begin at 17:15. So, and this will be posted on the website. But anyway, so this is the changes. Please be aware. So then for today we are done. Thank you very much, everybody, all the speakers and also all the audience. So then